Okay, so welcome to lecture 3 of course EN 203, and so far we have discussed few things regarding our system, what we need and why we are doing digital electronics, and then some things we started understanding about the number system. So obviously because we are dealing with something which is discrete and has two states, so we have a different number system. So we discussed a general, that is how it can be written or how we should read it. So we know that we have position based number system, and any number can have these properties. Number system can have these properties what we have discussed in the previous class. So it can be expressed in general format as this, where di has the restriction what is given over here in the inequality. And we can take that number, expand it, and get it at our natural radix, that is r equal to 10, the base radix what we have naturally in this world. Okay, so again videos are dropping. Why? Don't turn off your camera. Okay, so then we have gone to see that if we have well-defined base of 10, then we can have system of r equal to 2 or base equal to 2. And we know that the elements in this number system would be only 0 and 1. And with this we can form any number. Of course, there will be more number of places we need to have in this number system for representing any number. For example, this 1011 at base 2 means only 11 for the base 10. So we can transform from one base to another base given that we follow the rules what we have discussed. So we have gone to discuss like some other radix systems like 5 in general. So we can have all these things. Then we also saw some properties like how the number on the higher position changes corresponding to the lower position numbers. So whenever the lower position number rolls for 0 to r minus 1 times, then the next number changes. So when it completes the full cycle. Then we have the maximum number what we can represent. So this is the biggest integer what we can represent in this number system in the base equal to 10, and the total numbers what we can have is 10 raised to power n. So this is including 0. That's why we have minus 1 as the biggest integer. And this is how the nature of the counter would look like in any number system in general. So then we saw that if we are having this radix system equal to 2, then we are spending too many positions for representing any number. So we can have a different radix system. Let us say we can club 2-3 places and we can represent that. So going by that, we have seen that the process which was taking so many steps over here, let's say a number 179 we want to convert to some base 2, so it's taking so many steps, and finally the outcome is also a little bit lengthy. So we want to simplify this, and so we have started clubbing, so maybe 2 bits together, or we can have 3 bits together. So the 3-bit combination, this is little bit famous compared to any other thing. So here we say that when we have 2 raised to the power 3, so then our base r equal to 8 comes up, which is called the octal number system. So here we have 0 to 7 integers in this number system, and we can represent any number between 0 and 7 with 3 bits that we know already in r equal to 2. So this all we have seen, and we have also seen that the same number which was represented in binary system can be converted to r equal to 8 or octal number system with fewer number of digits. So here we call these as octal digits. Of course, we have not too many terminologies for this term. So we follow like digit for a decimal system, octal digit for the octal number system, and if something else comes, then I will inform you. So this is all is there, and then we are trying to convert few numbers to the base are equal to 8, and we see how we do. Sometimes when there is shortage of bits, we add something, we add 0 at the MSB, and we complete the groupings 3 bits together, and always start the conversion from the least significant bit side, so that you don't miss any information in the end, and you don't add anything extra also over there. So these are some rules for r equal to 8. Similarly, now when we are having 3 bits together, so I would say that a more popular and more universally accepted number system is perhaps the hexadecimal number system, where we have 4 bits taken together and the radix is 16. So of course, we have a bigger base value, so we can accommodate all the numbers in a very concise manner. Now, let us see what are the properties of this hexadecimal number system, how to convert, and what are the advantages. Then quickly we will go towards other number systems and all. So here r is equal to 18. Then what are the possibilities for the digits? So here we call them hexadecimal digits, or simply we can call them hex digits. Now, what are the possibilities? Can someone tell?
So 0 to 9,
0 to 9, 8,
and then
9,
alphabets
0 to
A,
15.
B, C, D.
Yes, yes, good. From your previous experience, some of you know. See, we have only numbers 0 to 9. After that, we need at least some symbols, some letters to represent the higher numbers, because we can go up to r minus 1. This is the maximum integer or maximum number what we are going to have in one place. So we have filled the 10 places, 0 to 9. Now what about the rest 6? So we take help of
Alphabet.
alphabets, yes.
A to F.
Yes, so we go by adding in sequence A, B, C, D, E, F. These 6 letters we add, and these have fixed value. When we talk about hexadecimal number system, A represents 10, B represents 11, C represents 12, D 13, E 14, F 15. Getting my point? This is the additional feature of this hexadecimal number system. We are going beyond this decimal number system, or r equal to 10 number system. So of course we can accommodate the bigger numbers in a very concise manner, in a crisp manner, or in a shorter format. So this is what we do. Now, if we take some examples, let us say yesterday's example only, if we take what we have done. So if we have to convert the same number, let us say, and yes, of course, when I'm saying this, another thing just to mention that this is the highest integer what can be represented in a 4-bit number system. So we are clubbing 4 bits together of the binary system. So this is the highest integer. F is actually 1111 in the binary system, and which is actually equal to 15 in the absolute number sense. So we are utilizing all the 4 digits and all the possible numbers from 0 to 15 in the 4-bit position system. So having said that, then we have the example what we took yesterday, 1 0 0 0 1 1 0 0, then 1 1 0. Let's say this is the number at base 2, and this we want to convert to our hexadecimal number system. Then we have to club 4 bits together. Now you see this. The 12 bits now will come down to only 3 hex bits or hex digits. So can you tell what these numbers would be? Yes.
8.
Sir, 4, 6.
Where are you starting from?
From
Sir,
left
from the
side.
left.
We have to start from here, the least significant bit, always.
Sir, E.
Otherwise, you will.
EC8.
Yeah.
E. C. 8.
Sir, E.
Okay.
C8.
C.
Hmm.
8.
8.
This is the correct one, right? Because we know these places have the value what we have learned in the previous classes. This is corresponding to 2 raised to power 3. This corresponds to 2 raised to power 2. And this corresponds to 2 raised to power 1. This is 2 raised to the power 0. That is how we compute the values, right? So 8, 4, 12 and 2, 14. So that goes to E. This is how we compute. We are clubbing 4 bits together and we are simply writing the number which corresponds to that particular value. Understanding my point? For example, this is simply 8, 4, 12. So 12 corresponds to C. So C is over here. Whatever is within 9, that number we can write straight away. Clear? Yes or no?
Yes, sir.
Yes.
Yes, sir.
One more example we take, let us say little bit more lengthier number, 111, 011, then 011, then 101, 010 and 01. So I don't know how many bits are there. 4, 4, 4, 4 and yes. So 17 bits are there. Nice. So yeah, now let us convert this. So how will you pair? These you always start from this side. So 4 together, then again we have 4 together, we have 4 together, 4 together, and now only 1 is remaining in the end. So what we would do?
3, 0.
Add
3
zeros
zeros
to the left.
From the list
Add
digit.
3 zeros.
List.
3
So
0
we
before
will
that.
add extra bits.
9.
We will add 0 as the extra bits and we will complete that set of 4 bits. So now tell me the number, what it would be.
So 9A.
9A.
A.
How is
B.
8?
B.
B.
This is what?
10.
A.
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 This?
B.
9A,
B.
B1,
Ah, then
D.
D.
E.
1.
fine. Any confusion in this?
No,
Any confusion? So what we are doing, we are simply pairing it up in 4 bits and then we are converting it to the corresponding hex number. This is very simple. Now I tell you the advantages of all these number systems what we are having. First of all, once you have any higher number system, let us say octal or hex number system, any number is given and you have to convert it to binary. This is the most trivial job, I would say, because let's say we want to convert it back, the 8CE hex into binary. We want to convert that. Now what would you do?
First convert into decimal, then in binary.
Okay. What other option we have?
We can club.
So we can write the code for each digit in binary form.
Exactly. This is what? See, 8 is what? 1000. This is done. Then C is what? How much is C?
1101.
1100. This is 12. Then what is E? 15. Sorry, 14.
1110.
1110.
Yes.
That's all. This is one-to-one correspondence with each set. Are you getting that? No need to go to any other intermediate number system or anything. This is very straightforward way because we know that this each number is actually represented by a set of 4 bits in hex system. So we need not go to any other number system or any other base to understand what this is. We can straight away convert to our binary system. This is the beauty of this. And here you need not worry whether you are starting from MSB or you are starting from LSB. Because this is fixed. You don't need to add anything extra or you need to remove anything extra. It's not like that. This is all fixed. How a number 8 is represented in hex, that is fixed. You know that 4 bits are used and this is the number. So straight away we can replace. And the same goes with the octal system also. So let's say I have the same number what we took yesterday, 4316. Now in octal, how would you convert it to binary? Yeah.
Each digit
Same.
corresponds to 3
Yes.
decimal binary bits.
Yeah. So tell the answer.
So
100,
100.
Oh.
1 0
uh,
0
then
1
11,
011,
010,
0 0 1
001, then
110.
1 1 0
that's all,
1 1.
isn't it? Each number corresponds to this particular set. Need not worry about from where you are starting. It is done. Now, the advantage when you are dealing with bigger numbers, let us say I asked for your roll number, right? So can you tell again any other roll number?
2011
Okay, 2011,
5002.
9002, is it?
Sir, 5.
5002. Okay. Now if I ask you, you convert it to binary. Imagine how many steps you will have to do for converting it to binary. First of all, how many bits would be required for this? How many bits would be
26 or
required?
27.
Hmm?
26 or 27.
Correct. 2 raised to power this. So the number of bits which can accommodate this is so high, which means so many times you have to do that division by 2, division by 2, division by 2, and so on. Now, the trick is if you convert it first to hex system. How do you convert it to hex system?
Divide by 16 instead of 2.
Yes, whatever rule we have seen for r equal to 2 is perfectly applicable for r equal to 16 or r equal to 8. Now, whatever number of bits were required for binary, that will reduce to 1/4 or something, no, for the r equal to 16. Isn't it? So effort for converting this number to hex will be much lower compared to the binary. And then from hex, you know how to convert it to binary. That's a straightforward step. So if by chance in examination, if you get a very big number, I am telling this trick once only. After that, I will not repeat. Don't ask me, sir, it's taking too much time and it's just 1 or 2 marks question and it's taking so much time in solving this. I have told you the trick. Fine. You can have some other trick also. You can go for any other higher R, let us say 32 or 64, and then you can come back to binary. So this is all for the smart people. You can apply your brain over there. Fine. Don't waste 1 hour, no, before that 2 marks question and then complain later on paper was lengthy. So this is the trick. Now again, same rule, whatever we have learned for r equal to 2 applies for all the other bases. So which means if let us say we have this number 1CE8 and this is hexadecimal number system of course, and we want to convert it to decimal number system. So how would we do?
So multiplying consecutive power of 16.
Sigma Ti r to the power I. First to binary, then to decimal.
First to decimal, then binary.
Yeah.
First decimal multiply.
How would you convert to decimal? That is the question. That's all.
So multiply by 16
Sigma TI
power
R to the
rates.
power I.
Yes, we have to go by the powers of 16. That's all. So 1 into 16 raised to power how much?
3.
3.
3 plus what is
12
next?
into 16 to power 2
12 into 16 square.
Plus
plus 14 into 16 to power
14
1
into 16.
plus
plus 8
8
into
into
16 to power 0.
0.
what's the number?
7400.
74.
700.
Good. Clear? So don't start doing all the unnecessary things in the examination. If I ask you to convert to decimal, this is always applicable for any base as long as you follow the rules. Understanding my point? Lot of people
Yes,
have again turned off their camera. I will again tell you, insist that you turn on your camera. The responses have come down actually. If you are feeling sleepy, please tell me. I can arrange for coffee or tea also, if you want. No, I just have to tell your parents, that's all. Nothing much I will do, don't worry. Then perhaps you will prepare for yourself also and for them also. That's a different thing. But good, at least your sleep will go away. Okay, so this is done, right? We have understood how to utilize any number system, whatever we are learning. The biggest of the numbers also, we can convert to binary or any other number system very easily if we follow the proper rules and we follow the proper conditions. We apply the logic correctly. Understanding my point? This whole course is about applying the logic or reasoning. So you have to do that. Now, let us see some more interesting things in this. So, okay, I will not go into too many examples. Let us skip all that. Now, let us see how we can represent if we have negative numbers in our application somewhere, if we are encountering those, how to represent that. So, again, taking example from what we know. So how do we represent a negative number in our general number system?
Using a minus sign.
Yes. So we have, let us say, two things in that number. One is some symbol we give, and then we have the magnitude. Isn't it? We have, let us say, 85 and we write plus 85. Then this strictly means that this is a positive number. Similarly, we can have minus 85. So this is the symbol which we are using to represent positive or negative numbers. Understanding my points? So many a
Yes,
times
sir.
what happens that we, even if no sign is there, what do? We take it as a positive number. But specifically for negative numbers, we must have this symbol. That is how we correlate with things in our life. No, we have, let us say, vector quantity to represent. We will have always some unit vector and its magnitude. So some k times of a hat, that we will say is the vector a. That is how we see things which are direction or which have the polarity we are going to encounter in our system. So when voltage is there, you talk about AC voltage, it's changing from 0 to 230 volts or 325 volts peak, comes down to minus 325 peak and then goes to 0. It's changing its polarity. So now the same thing we want to extend to our digital system as well. Now, how do we do? And
So
another,
use a bit as a reference, or like if in binary use 0 as Positive and 1 is negative.
Yes.
Any bit
absolutely.
we can do for left most significant digit.
Yes, that's true actually. So before that, we have, let us say, number 0. So even for this, we have two possibilities, isn't it? We can write plus 0 minus 0. Both have the same value. There is no change in that. But when we are representing the positive and negative numbers and we are using this sign, then of course we have two possibilities. Whether it has the same value or different value, that is the next thing. So again, we may have some number system where we will have two representations for 0. Sometimes we will have number systems where we will have only one representation for 0. This you keep in mind. This is in general true for different number systems. Time to time we will discuss this thing. Now coming to what he was saying, yes, of course, we use a bit because ultimately what we have only ones and zeros in all our system. We cannot have plus or minus or any other symbol over there. It's only yes or no. So this yes or no only we have to use as our reference for the positive and negative numbers as well. Getting my point? Now let's say a number is there. Let's say we are representing 85 as 01, 01, 01, 01. This is the number which we call as 85 at base 10. What we see when we are referring to its magnitude and its sign, we refer to the most significant bit. And we see whether this is 0 or 1. And that signifies whether the number is positive or negative. If the most significant bit is 0, then the number is positive. If the most significant bit is 1, that means the number is actually a negative number. So the value is actually represented in the remaining bits. This is the magnitude of this number. The last bit is only there for the sign convention, what we are having. So same number, if you write as 1 and then you write 1010101, then still the value is this, which is unchanged. But because this 1 is there, so we can say that this is actually representing minus 85. This is in some random number system. I am not saying this is how we follow our things in our digital domain, but this is one example I am giving. So this we call as sign bit. Yes.
Why its value not changing?
What else
We
it can
introduce
be?
one.
Yeah, what else is it can be? Yeah. Can it be anything else other than 0 or 1?
No, sir.
Then if anyway by default we have been saying that our 0 and no any general number is having this magnitude, then of course if we want to change it to negative number system, the highest bit or the most significant bit we are changing to 1, that's all. That we call a sign bit. If sometimes we don't have sufficient bits to represent the negative number, we add another bit, extra bit over there, and that we call as sign bit. There are only two options. So that is how it is given, 0 for positive, 1 for negative, that's all. You need not confuse in that. Clear? Yes or no?
No, sir. Its
No.
value will change, sir, if we add one in the one as bit in the most significant digit.
So you want 1 as the positive number, right? What do you want? What do you want to change it? Yeah, Rajendra, quickly.
So he is saying that if we have 1 in that position, then it should be like 85 plus 2 to the power 7.
Yes,
sir.
exactly. But then when we have such number system where we have possibilities for negative numbers, we change our way of reading these numbers also.
Okay, sir.
Here we have not gone by the conventional way of reading this. Here we are taking it as only sign. That's why I said this is magnitude, which is common in both the places. Here you read all that 2 raised to power n minus 1 and all that. This is true for all other bits which correspond to magnitude. But yes, there are ways when we can include all this as 2 raised to power something, and then we can compute and it will come as a negative number. I will come to. Fine. This is just one example I have given. How you can see or look at the negative numbers in digital domain. Fine.
So we distinctly define the magnitude as well as the sign.
Yes.
Yes.
That is all. This is just an example. I'm not saying that we.
In the second example, the leftmost one is not included in the magnitude.
Okay, is it?
Okay, sir.
Leftmost one means what? The sign bit, right?
Yes.
That is what I'm saying. Don't include in the magnitude. That's the sign bit. That is the MSB. This is what I have been saying.
Yes, sir.
Okay. So now, when we have, let us say, positive and negative numbers, both we are representing, of course, the biggest integer and all what we have been saying that we can represent 2 raised to power n minus 1, all this changes. So now it becomes half of that almost. So this is the highest negative number and this could be the highest positive number. Sorry. So, okay. So these could be the highest positive and negative numbers what we may have in the number system when we have both positive and negative numbers coming in our n-bit number system. Is that clear? Of course, that will get reduced because 1 bit we are only using for the purpose of sign. Clear?
Yes, sir.
No confusion in that, right? Now, how do we actually represent our negative numbers? So we don't call the negative numbers as negative numbers. We call them as complementary numbers. So what is meaning of complementary numbers?
When added to their positive values, they get 0. That's
Exactly. This is the exact meaning of complementary. If you are having x plus x and you are adding minus x to it, you will get 0. And this must be true whichever way you are defining your complementary. So this minus x is complementary to this plus x. Understanding my point? Now all that confusion of how we are reading this sign bit and all, this will go away. So there are two ways when we are having this complementary number system. In two ways we can generate this. First method is we have radix complementary. And this is true in general for any number system. Let us say any number d is given, which is having n bits, so dn minus 1, dn minus 2, and so on up to d1, d0. And we have to write the complementary of this. Then this is for radix r we are talking about. This can be simply computed as r is to the power n minus d. This is in general true for any number system where we are generating the complementary number by this rule, which is called as radix complementary rule or radix complementary system. Understanding my point? For example, let us say we take this number 1849 at base 10. Now this is our number and we want to generate the complementary number. So can you tell what it would be? 10 raised to the power 4 minus 1849 at base 10. Yeah, so how much it would be?
8151.
At base 10. Now how do you say these two are complementary? Add.
Changing to binary.
The rule must
Sir,
be
adding them is 10,000, which will
Yes.
actually become 0.
So here we are talking about 4-bit system, no? 4-digit system.
Yes.
So we have 4 significant digits or bits over here. So whenever we are adding, subtracting, whatever we are doing, ultimately we will have 4 digits only or 4 bits only. So if you add, this carry forward will be ignored. That is not part of the system. So where we have come back to, we have come back to 0. So this is how we define our complementary number system in digital domain or these kind of number systems. Now there are better ways to compute. You need not go, let us say some very big number is there. You will be, taking the power and subtracting and all that. So that's okay. Nowadays we have the calculators and all, but still there are better ways to do this. Now here, one good example would be if you want to compute the complementary of 0. Again, let us say there are 4 significant digits. So now can you compute what would be the complementary of D?
The same.
10 to the power
10.
4.
10 to the power 5.
Actually, ignoring the last bit, we have again 0. So that is why I say in this number system or in this radix complementary system, we have only one representation for 0. So I was talking about 2 different representations sometimes. Here we have only one representation for 0, which is actually 0, 0, 0, 0. Getting my point? Okay, now let us see some better ways to do this, the same thing, and then we will extend this for our binary system also. Now actually what we are trying to do, if you expand this, the complementary is nothing but, so we can write it in a little better manner. Getting my point? I have only taken away 1. Now, what is this number? R raised to the power n minus 1.
Maximum number of the system.
Yes, this is the highest integer what can be represented with the n digits or n bits. Getting my point? Now, what is this actually highest number? Let's say we talk about radix r. So the highest number would actually have all digits r minus 1, r minus 1, r minus 1, r minus 1 and so on. Isn't it? For all the n places? For simplification, let's say small m is equal to r minus 1. So basically this r raised to the power n minus 1 is nothing but this repeating series of m for n places. Getting my point? There?
Yes.
Or bouncing little bit? Yes or no?
No, sir.
What is no?
How are you representing Rn minus 1 as product of R minus 1?
Again, don't see as product. I am saying these are places. These are n places. Like you are writing any number, let's say for r equal to 10, what will be the highest number represented for 4 bits? It would be 999.
Yes.
So I'm telling for in general any r, if m is equal to r minus 1, the highest number would be this repeated series of m for n places. Any confusion in this?
No,
Now,
sir.
when you are doing this subtraction, again, you see carefully. When you are doing this, basically what? Each and every number of this d, which is dn minus 1, dn minus 2, and so on, is getting subtracted from this number m. Isn't it?
Yes, sir.
It need not borrow anything from the previous because this is the highest. At the most, the di could be equal to m. That's all. So it's like independent subtraction you are doing for each digit. And you are getting the result and then finally adding 1. So that is why for r equal to 10, let us say if I take the specific case of r equal to 10, we call this system as this will be 10's complement because this is full. So what we will do over here, let us say again, if I take the same example, 1849 at base 10 as this number, what would be d complement? So you subtract 9999, whatever number comes, just add 1 over there. So tell me, this will be 0, 5, 1, 8 plus 1. What is this? 8151, what we have got in the previous computation. Got the point?
Yes, sir.
Yes, sir.
Yes, sir.
Getting the point here clearly? Same thing, if you say for r equal to 2, what would you call it? 2's complement. So what you basically do, let us say any number is given b, let us say 0001, 0001, and you have to get the complement. And what is the number? This, let's say, is 17, I think, right? Is it correct?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So what would be the complement of this? Complement of b? Okay, I think once again I need to remind you
So first we find the one complement
83
and then
plus
add
1.
1.
83.
No, wait. I think once again I need to remind you to turn on your cameras. Again, very few people are there, including me, some only 5, 4, 9 to 11. That's all. Yeah, I'm watching you. Don't worry. I'm doing the conversation with all of you. This is the state as of now. Okay, the moment it goes beyond some threshold, I will point it out. So turn on your cameras. Fine. Now the answers.
83.
83. 82 plus 1.
What is 83?
111.
Yes, you have to tell the bits 1110, 111
0, 1,
plus 1.
Yes, sir.
plus 1.
Getting my point? So what it will be 1110, 1111. This is the complement of this. Understanding my point? Now here, how to read this bit, the last bit, because we have merged everything together. Now we are not saying specifically that something is sign bit, something is no magnitude. We have merged everything together in this complementary system. We are only telling this is the complementary of some number. This is the complementary number for this number. So how to read this bit? So now the weightage for the last bit would be minus 2 raised to the power n minus 1. The rest all would remain same. Getting my point? So obviously when this is 1, this would come in picture. When this is 0, this would not be there. Getting my point? Now can you compute with this information what is the value of this at base 10?
So minus 17.
It should be, otherwise it's wrong. So this is what you compare. If you have not done, then you do and check it. So you will find that exactly this will be minus 17. There is no ambiguity in this. Am I clear?
Yes, sir.
And you can verify. You can verify by adding these two numbers together, b plus b complement, and you will find that you will have all nicely 0, 0, 0, 0 sitting all over. Can you see that? May have some carry forward or something,
Yes, sir.
but that will be ignored. So this is 2's complementary system or radix complementary system. When we say 2's or 10, or we can have 8's or 16's complementary system, in general we call this as radix complementary system, where we are having this kind of approach, what we have taken. And the speciality of this complementary number system is we have unique representation for 0. Am I clear?
Yes, sir.
Now let us go to the other way. So some places it is also used, the other way of representing the complementary number system, that is called diminished radix. In this system, again, only one difference, nothing much. The complementary number is this, that's all. So compared to the previous one, this extra -1 is there, that's all. But what that will do? That will ease out all the complications in the previous one. Let's say 1849, you have to take complementary, what you have to do? You have to simply subtract all the numbers from 9. So the D complementary would be 805, is it? 8150.
8150.
That's all. That will be your complementary numbers. Now here the thing is that we will have two different representations for zero. What will be two representations? You can check yourself. Let's say we have to find out the complementary of 0, 0, 0, 0. Now can you tell what is D complementary?
1, 1, 1, 1.
9, 9, 9, 9. And it's not overflowing. Please mind it, this is not overflowing. So if it has to fit the rule that D plus D complementary equal to 0, 0, 0, 0, and this one has 0 value, then which means this is also having a 0 value. So that is why I say in this system we have two representations for 0. Understanding my point? These both are called as 0. For example, if you add these two numbers, the previous example, these two numbers, if you add, this will also end up in 9999. This is regarded as 0, as good as 0. Understanding my point? So for specific radix cases, when we talk about r equal to 1, sorry, r equal to 10, these are called 9's complement. Because we are simply subtracting from 9. For r equal to 2, we call as 1's complement. We are simply subtracting from 1. That's all. Clear? Is that clear or not? See, this is 2-hour session, right? Why are you started feeling dull suddenly. This is a 2-hour lab session, right? Or do you want me to stop now? Honest answers. I don't mind.
Sir, if possible, you can end the class now.
Okay, that's a very polite and honest answer. Good, I agree. More than certain information you cannot process, and sometimes you don't want to process. That is another thing. That's okay.
Graph of concentration goes down.
Okay, that's great. What is the graph of your concentration? I know everything going on, and one sudden some message or something comes, all concentration goes down. It's very, very discrete. I know that. So it's not continuous. Don't tell me that it is gradually reducing. It drops suddenly with any small disturbance. Anyway, just one small thing I would tell, and then we would stop over here. So all other things I think you can do on your own, or some things we will do tomorrow during the tutorial. So let's say only one binary example we can take, this 00010001, and we have to find the ones complement. So we can very well write like this. This is the complementary of this, and of course if you add this, this is 11111111. This is another representation for 0. So don't forget, when you are doing ones complement and when you are doing twos complement, if you add the numbers, you see the difference, don't worry. This is by rule they are getting like this. And the most famous and most universally accepted system for complementary numbers is the radix complementary system. It's not diminished. The radix complementary system is the more popular one, and it has its own advantages. So to summarize everything, what we have seen, that if we have to plot a graph for our numbers, let us say we take a 16-bit number and we express it by some 4 hex digits, and we have to plot its value, magnitude and the sign both. So if we start from 0000, and this is hex, and all the way we go up to 7FFFF hex, and again all the way we go up to FFFF. So how this would look like? Just a glimpse of how you should perceive the numbers or values. So it will gradually increase from 0 to 7FFF, and then suddenly it will go down, and again it will start. In magnitude it will be reducing, but in value it will be increasing, and it will go and touch 0. This is how the nature of number is in this digital domain. I have taken 4 bits, 16 bits of binary, 4 hexadecimal digits, but anything you can take, in general it will have this kind of nature in the complementary system what we have learned. Clear?
Yes, sir.
Okay, so then we can stop over here now. Any doubts, any questions you have, you may ask.